equations of state would produce P versus V charts which have only one real solution for temperatures higher than the T critical, at the critical temperature we have a double root actually we have all three roots together, and at temperatures less than T critical we have this profile also temperature less than T critical. And the way you use that, you go to a pressure. So at higher pressures, for example, let's take the case where we have a possibility of multiple phases in coexistence. So if I'm at high pressure, I will have only one solution. Here, let me redraw it with just this. This is T less than T critical. So at high pressures, I have only one molar volume, then you are only in the liquid phase. At very low pressures, I also have only one molar volume, that's vapor phase. But there is a region where I can have three solutions. The lowest solution is the liquid. The highest molar volume solution is the vapor. And this one is an unrealizable steady state. As we saw in the previous lecture, it violates the condition that KT must be positive. This one has KT negative, violates stability. So this can never happen. In reality, of course, this is what the cubic equations of states give us. In reality, what you have is liquid at high pressures, and at this specific pressure where you have coexistence, that's the vapor pressure. At the vapor pressure, and only at the vapor pressure, you have coexistence of the two phases, and at lower pressures, you have liquid. We have vapor. Vapor, liquid, coexistence. Yes?
You're saying at that flat line there's both?
Yes.
Okay.
What would happen is, let's say I take water, maintain at a constant temperature, and I vacuum out all the gas and then seal it. What will happen is water will evaporate until the pressure becomes equal to the vapor pressure. Okay, clear? And also, the Lever rule applies everywhere. So if you are at the vapor pressure and you have a mixture, the two phases coexisting, the mole fraction of the vapor, so here, Lever rule applies. So if you have a mixture, molar volume, something in between here, the mole fraction of the vapor phase, mole fraction, is going to be equal to the molar volume of the mixture minus the molar volume of the liquid phase over the molar volume of the vapor phase minus the molar volume of the liquid. Okay? The same thing, the same relationship would hold for enthalpy, entropy, Gibbs free energy, and so on, all thermodynamic. Another way to say this is the molar volume, if you have a certain mole fraction of vapor, turn it around, this gives you the molar volume of the vapor phase, of the mixture, sorry. This is the molar volume of the mixture. If you have omega, vapor fraction, molar fraction, then the mixture is going to be equal V liquid plus the mole fraction V vapor minus V. Okay? Similarly, H mixture would be H liquid plus omega H vapor minus H liquid. Okay? That's the liberty. Any questions? Okay. And the other thing we reasoned out Monday was that if I have two phases in equilibrium, I must have equality of the Gibbs free energy between the two phases. So Gibbs free energy here must equal Gibbs free energy. So these diagrams are each for a given temperature. A PV diagram for a given temperature. I know that I must have, at the vapor pressure, molar Gibbs free energy liquid equals molar Gibbs free energy vapor. Okay, must have P vapor must have and this is a vapor pressure at a specific temperature. So this is at a given T. And we know that dG is minus S dt plus VdP. So at a given temperature, temperature fixed becomes VdP The next thing I'm going to do, I will show you that given any such graph, given any graph PV like that, we can find out what is the vapor pressure by finding the straight line at which the pink volume equals the blue area. At the vapor pressure, the pink area must equal the blue area.
Is that because we realize it's just a line? We have to like subtract.
I'll show you in a minute. So, at P vapor, A1 must equal A2.
Wait, I thought P vapor was just any area in between both minimum and maximum?
No, for any given temperature, there's one unique vapor pressure.
P vapor, right?
Hmm?
That's what you call P vapor, right?
You have
No.
3 solutions here, okay? But you will have the 2 phases coexisting really only in the vapor pressure. Now, when we talk about droplets and bubbles, you can have subcooled vapor or superheated liquid,
Oh, so if you
So-
drop below that,
but there is
Pressure.
only one vapor pressure, and the vapor pressure is when the 2 areas are equal.
so if you drop a little bit, it would go to liquid?
Yes. So basically what it does is only liquid, coexistence, only vapor. So not going negative. Yeah, okay, that's the end of that. Only vapor. Okay? But here you have 3 real solutions above here. But of those solutions, the vapor pressure is when the 2 areas are equal. So let me show you. Okay. So the first thing I'm going to do is, because I have integral, so what is G? G, at the particular temperature that we're interested in, any pressure is going to be what I have at the reference condition, at the reference pressure, plus integral from P reference to P of VdP. And the integral is a definite integral from the reference pressure to whatever pressure I am. That's the area under the curve. If I have a V versus P diagram, this here is definite integral of VdP. Okay, if this is P reference, and this is P here, this is specifically I'm using this P. And this is V molar. So V molar against P now, not P against V. And I'm interested specifically if I put here P1, from P reference to P1, the area. Okay, calculus 1. Okay.
All right, last question.
Problem?
Yeah. So if you're in the middle of where the dimple is, you have like a little bit, like mostly liquid and vapor, which is liquid, because your tie line says.
Okay. Liver, if you're here, if your molar volume is here, you have the fraction of this guy, which is liquid, is the ratio of this distance to this distance.
Okay.
And the fraction vapor is this distance to the total.
Okay. All right. Got it.
All right. So, that, and I have for G integral of VdP. So what I'm going to do is take this diagram and flip it. So I'll change it to VdP. So step 1, we flip the cubic equation diagram to have it as VdP. So I'll put V here and P here, and flipping it is really switching it like that. So that becomes okay. A little bit. And let's say that the vapor pressure is here. So our color specific for today. So let's say this is the vapor pressure. And let me put some symbols. Let's say P reference is somewhere on the left. And let's call this point A, little a. This point, little b. This point C. This point D. And this point E. What do we have? Here, high molar volume, that's vapor side. So right here, vapor. Right here, we are liquid. Here's the vapor pressure. We have coexistence between vapor and liquid. What we know? We know that at the vapor pressure, I must have molar vapor equals molar liquid. Well, at the vapor pressure, what is here? Molar of liquid, G. Of vapor, Ga. So I must have. So far so good? So I know I have a vapor pressure if G of A equals G of A. What expressions can I get now for G? What can I write for G of A? Well, I guess I raised the equation, but I just had written that G equals G reference plus integral from P reference to P of V molar dP, right? So GA is going to be G reference plus integral from P reference to P at A what is the integral? Let's say here is P reference from P reference to PA of VDB. The area underneath this curve here, between these two lines. So this area here this area is GA minus GF. What is it?
So you're taking P reference to be 0?
No, it doesn't have to be 0. GA minus GF.
Okay.
Whatever it is. Could take it 0, but okay. Okay. Let's calculate next what GC would be. GC is G reference plus integral P reference to PC VDP, and I can rewrite that integral, break it as the integral. So it's until the integral. Probably I should put just the point, save some time. So I'm going here, but the wave, this is the curve, I can write going here as going to A, plus from A to B, plus from B to C. So this is integral G reference plus you allow me to just write integral without filling the rest of it, saving a bit of time, plus PA to PB, plus PB to PC. So far so good? Okay, PA to PB is what? This area here, right? So the orange is integral PA to PB, the area underneath. So far so good? Drop it.
Is there any reason not to go from reference to B, like instead of just doing it in two intervals?
This is